Alright, so we're going to end section 5.5 with two last examples just in case you want them. So here we have the definite integral from 0 to pi over 4 of tan cubed times secant squared d theta. Now we're going to use u substitution here, and what I'm going to do is, well, I'm just going to notice that, like, I have tangent here and I have secant squared here. Well, I know that the derivative of tangent is secant squared. So I am going to let u equal tan theta, which means that du is going to equal secant squared theta d theta. Great. So remember that it's not enough to just substitute u in for the function in my d theta. I also want to change my bounds. So my new lower bound, or I'm sorry, my new upper bound, well, that's when I plug pi over 4 in for theta. So what is my new upper bound going to be? It's going to be, if I take tan, and I plug in pi over 4, that's going to give me 1. And my new lower bound, we'll curse it out, would be tan of 0, which is just 0. Wow, so I changed my bounds from 0 to pi over 4 to 0 to 1. Remember, these bounds are in terms of x. That means that x goes, or no, I'm sorry, not x, theta. Theta goes between 0 and pi over 4, but since I'm changing everything into terms of u, and u equals tan of theta, that's going to change my bounds. So, when I take all this information, let me just go ahead and quarantine this off, I take all that information and plug that into here, what I'm going to get is I'm going to have the definite integral from 0 to 1. Remember, tan is u now, so it's going to be u cubed. Secant squared theta d theta, well, that's just du. Now look how much, like, instantly nicer this looks than this one. So that is going to be u to the fourth divided by 4, and I need to evaluate that from 0 to 1. So what that is going to be is that is going to be 1/4. Wasn't that nice? Like, when I first looked at this, I was like, oh my goodness. But no, it's actually not so bad. So let's take a look at one last example that uses u substitution, but we're going to take a little bit of a tangent, no pun intended, and look at some more trig stuff. So let's say that we have the definite integral from negative pi to pi, and let's say that we have cosine squared x dx. So the first thing I'm going to tell you is that if you look at this guy, you can try to let cosine equal u, and it's not going to get you anywhere. You can try to let x equal u, and it's not going to get you anywhere. So what we're going to do is that I'm going to look through some trig identities and see if there's anything I can change out for, well, not with the dx, that I can change out for this cosine squared of x. So when I look through my trig identities, what I see is that cosine squared of x can be rewritten as 1/2 times cosine of 2x plus 1. So what I'm going to do is that I'm just going to rewrite this so it just looks a little bit nicer. So let's rewrite this. Remember, I haven't set anything equal to u, so I don't need to do any substitution yet. So this integral is going to be negative pi to pi. And remember, that 1/2 in front, that's just a constant, so I can throw that out in front here and just kind of forget that it's there. Cosine of 2x plus 1 dx. So now what I can do is that I can take this guy, and what I can do is I can let that be my u. So let's go ahead and do that. Let's say that this 2x is my u. So u equals 2x. And when I take the derivative of that, I'm going to have du equals remember, I don't have a 2dx over here, so I'm going to divide both sides by 2, which is the same as multiplying by a half. That's going to be 1/2 du equals dx. Alright, so now what this becomes is this is going to become, oh wait, I almost did something awful. The something awful I almost did is that I forgot to change my bounds. Oh my Lanta. Okay, I almost really goofed this up, but I didn't, so we're okay. So, my new upper bound, well, if I take pi and I plug it in for this x here, I'm going to get 2 pi for my new upper bound. And if I take negative pi and I plug it in for x here, then for my new lower bound, I'm going to get negative 2 pi. Which, granted, is not as nice as the last one, but it'll do. So, we're going to have 1/2 the integral from negative 2 pi now, that's my new lower bound, to positive 2 pi, that's my new upper bound, of cosine of u plus 1. And remember, instead of dx, what am I going to have here? I'm going to have 1/2 du. Which I can take that 1/2 and what can I do? I can shove it out in front. So it's going to be 1/4 the integral from negative 2 pi to 2 pi cosine of u plus 1 du. Now this actually isn't too bad because I know the antiderivative of sine, or cosine, is sine, and the antiderivative of 1 is just u, so I need to evaluate that guy from negative 2 pi to 2 pi. Great. Which is going to give me, so what we're going to do here is that we're going to evaluate this, so that's going to be 1/4 times, and we're just going to let that 1/4 thing out, so it's going to be 1/4 sine of 2 pi plus 2 pi minus 1/4 times sine of negative 2 pi minus 2 pi. And if you do the arithmetic on this properly, what you're going to end up with, and it just blows my mind that this works, you're going to end up with an area of pi. Isn't that crazy that it ends up being such a nice number? Yeah, so those were the last examples I wanted to